Alright, hey class. Okay, so today we're going to do a quick and dirty on how to determine which intermolecular forces are at play. So as a quick review, let's talk about the different intermolecular forces. So we have London dispersion, dipole-dipole, and hydrogen bonding. So for London dispersion, remember that's the weak one that's between two or more nonpolar molecules, and it's very, very temporary. Okay, remember it's talking about the temporary shift in electron density, which causes a temporary partial charge. Okay, a partial charge closest to whoever's the more electronegative. So in this case, like say hydrogen. Okay, so you have a hydrogen molecule, and the bond consists of two electrons. That's cool. Well, what about if at any given moment the electrons decide to move over to the left hydrogen? What happens then? Well, this guy then forms a partial charge. Now, because he has all the electrons, what kind of partial charge should he have? Very good. Negative. Okay, which means that he would be left with a partial positive charge. Alright, and so that temporary shift in charge and those temporary partial charges are what form the bonds between other molecules, other nonpolar molecules. Now the difference between that and dipole-dipole is that for dipole molecules, those charges are permanent. So let's look at hydrogen bromide. Because hydrogen bromide is the more electronegative, he's the one who's going to end up with all the electrons, so he's going to be partially negative, very good. And he's going to be partial positive. Now, because that is permanent, that hold that they have between other hydrogen bromides is going to be a lot stronger than London dispersion. Remember, dipole-dipole is kind of like a marriage. And then the last one is hydrogen bonding. Now, hydrogen bonding is very similar to dipole-dipole. It's like right underneath it. The only difference is that the hydrogen needs to be involved, one, duh. The second thing is that it needs to be bound to either fluorine, oxygen, or nitrogen. If it is not directly bound to either of those, then it is not considered hydrogen bonding. So something like hydrogen bromide, because that's not FO or N, it doesn't work. Okay, so remember fun, or for my first period, NOF. Alright, so what I did is that I drew a nifty kind of flow chart to help your thinking when you're addressed with these kind of questions. Alright, so the first thing that you have to ask yourself is whether it is a a 2-atom molecule or a 3-atom molecule. Now what I mean by that is it like HBr? Do you see how there's only 2 atoms involved? Versus something like ammonia, NH3. For this one, 4 atoms are involved. So that's what I'm talking about when I say 2-atom molecule or 3+. So once you determine what it is that you're actually working with, the second step is to see what course of action you're going to have to do. So if it's 2-atom, it's going to be dealing with the electronegativity difference. If it's 3-atom, you're going to have to draw the Lewis dot structure. Now, we're going to do some Lewis dot structures, but if that's what you're struggling with, then you need to watch the other video that I made, okay? So let's focus on electronegativity difference. I told you that if it was found within the range of 0 to 0.2, or between 0.2 and 1.7, then that indicates whether or not something is polar or nonpolar, okay? Now, if you're looking at Lewis structures, what you need to be thinking about is how many lines of symmetry do I have? If I have more than one line of symmetry, is it polar or nonpolar? If it has more than that, then what is it going to be? So, that's what you need to be thinking about. The first step is deciding which course of action am I going to take. Am I going to draw a Lewis dot structure, or am I going to figure out the electronegativity difference? And then the second step is to see whether or not my molecule is polar or nonpolar. Because unfortunately, unless you know whether or not it's polar or nonpolar, you can't figure out what kind of bonding it's going to be. So if it's found between 0 and 0.2, then it's going to be nonpolar. If you found it between 0.2 and 1.7, your molecule is most likely polar. Okay? So if you're looking at the Lewis structure, however, what you're focusing on are the lines of symmetry. So if you have more than one line of symmetry, and for example, let's say methane, CH4, do you see how I not only have one line of symmetry here, I have one here and here and here. All of those different lines of symmetry. So I don't just have one, I have plenty. However, for a polar molecule, let's look at water, for example. Do you see how many lines of symmetry do I have? I only have one. I can't cross it any other way. Same thing as if you have no line of symmetry. Some molecules you can't even put any line. Those molecules will always be polar. Now, once you figure out if it's polar or non-polar, that's when you decide who is it that you're at, what kind of intermolecular force is at play. So if my molecules are non-polar, what do you think that's going to be? Very good, London dispersion. If it's polar, well, that gets a little bit tricky because you have to think about what it is that's at play. If there is no hydrogens attached to fun, then it's going to be, very good, dipole-dipole, versus if it does have, so if it is attached to fluorine, oxygen, and nitrogen, then it's going to be hydrogen bonding. Okay, so let me erase this, and so that way you can see I put that into consideration. And so this is the type of flow chart that you need to be going through every time I present you with a molecule, okay? Start from the top and work your way down, okay? Most of the time I probably will ask you for a 3+ molecule, something like this. And so you need to be able to draw the Lewis structure. Ask yourself, does it have symmetry? Does that mean that it's nonpolar or polar? And then what kind of bonding does that mean for my molecule? Okay? Hopefully I didn't go too fast, but if not, feel free to rewind and go through it again until it finally clicks. So let's go ahead and just do an example. In this case, I chose CH2Cl2. Alright? So like I said, the first task is to draw the Lewis structure. Do you see how it has more than 2 atoms? So we need to draw the Lewis structure. So carbon is always in the center. And the cool thing about him, oh, I'm sorry. I should start with what is the valence electrons. I have to see how many cans of Coke am I bringing to the party. So go ahead and draw the Lewis structure if you feel comfortable, and then I'm just going to keep going. So it's going to be 4, 2, and then 2 times 7. So I add all of this together, and that's going to equal 2. It's going to be 6 plus 14, so it's going to equal to 20 electrons. Okay? So I have 20 electrons to play with. Well, carbon is always in the center, remember that, unless I tell you otherwise, or I draw it out otherwise. The hydrogens are going to be right there. Now the thing is that when I'm dealing with a molecule just like this, everything is going to be attached to the carbon. Okay, nothing's going to be left for the, nothing else is going to attach to something random, okay? Now, do you see how I drew the hydrogens together and then the chlorines together? Like sticks with like, so make sure that you don't try to separate people. It's like trying to separate siblings or something. Everyone likes to stick together, okay? Now, as you remember, hydrogen's pretty happy because how many electrons does he have? Do each of them have? 2. So they're done. Now we need to look at chlorine. So once I eliminate the 8 electrons from my bonds, see, 1, 2, 4, 6, 8, I am left with 12. And so what I can do is that I start on the outside and work my way in. And I ran out of room, so I'm going to write the last set up here. Do you see how with all these electrons I was able to get rid of those 12? And is my carbon happy? Why, yes it is, because it has all 8 from the bonds. Okay? So the next thing that we have to ask ourselves is what? Very good. Does it have symmetry? So, does it? Alright, well, I got one line of symmetry going this way. Do I have any other lines of symmetry? No. So because I have no other lines of symmetry, what kind of molecule is this? Very good, it's polar. So if it's a polar molecule, what kind of intermolecular forces could it be? Now I know you think that there's a hydrogen in there, but who is he connected to? The carbon. So the only option is what? Very good, dipole, dipole, okay? So the intermolecular force at play with my guy right here is dipole, dipole, alright? So that's how you're going to attack these types of problems. Now, let's think about what if it's only 2? Let's look at hydrogen iodide, okay? Now, I know right away you probably want to think hydrogen bonding. However, who is the hydrogen bound to? Very good, iodide. Okay? Alrighty then, so how many atoms are present in this? Very good, just 2. So if there's only 2, what is it that we need to be looking for? Are we going to draw the Lewis structure? Well, we can, but there's no real point. What are we actually going to focus on? Very good, the electronegativity difference. So in this case, I need to figure out what the electronegativity is of iodine and the electronegativity of hydrogen. So don't worry, I will provide you the chart, and right now go on Google or something to see what the electronegativity chart is. According to my chart, iodine is 2.5 and hydrogen is 2.1. Okay? So if I take the difference of both, what is my answer? Very good, it's going to be 0.4. Now 0.4, where does that lie into our spectrum? Remember, in my chart, I told you, I gave you 2 different options, ranges at least. From 0 to 0.2 or from 0.2 to 1.7. So who is our guy? Yeah, him. So that means that our molecule is what? Very good, polar. So if our molecule is polar, then what kind of bonds, what kind of intermolecular force are we going to be looking at? Very good. Again, dipole-dipole. Alright, so I hope this kind of helped. If you're still stuck on Lewis structures, go look at my other video. If not, try watching this one more time. Maybe it'll help sink in then, okay? Don't be worried. Don't be freaking out if I'm talking too fast. That's why you have a pause button, okay? Good luck.